last up is a significance test to compare two proportions. So looking at the same example from before where we asked men and women if they were willing to date younger people, and we had a certain number of successes where P1 hat and P2 hat were 74% and 28% respectively. And let's say we wanted to know, is there significant evidence to say that men are more likely to date younger people? And as we talked about, is probably strong evidence, but what's our p-value? And again, how would we go through calculating that p-value? But as usual, we have a formula for Z interval. And notice it's pretty much the same idea. You take the difference in the two sample proportions, and you take the difference, or you normalize it based on the standard deviation. Now, the standard deviation here, you could use the standard deviation from this one, the standard error, but you can actually be more accurate in using what's called the pooled proportion. And it's a more proper way of doing this. And the formula for what p hat is, I think this is a little poor notation because p hat is just the sample proportion. But in the context of a two sample mean, p hat always stands for the pooled proportion, which is just like the total proportion. So if you add them together, so like if you add the total number of successes divided by the total sample size, basically you remove the fact that some are men and some are women. Like if we just look at this full data, we have 100 people and we have 51 successes. So that would be a 51% success rate in general. And that's what p hat means when we're not separating our populations into two groups. So anyways, if we were to do this, again, we could start by calculating the Z statistic, and then we could use that to figure out what is our p-value. Again, different p, capital P. So Z statistic, let's copy down the formula. Z is equal to P1 hat minus P2 hat divided by the square root of P hat times 1 minus P hat times 1 over N1 plus 1 over N2. So plugging all of this stuff in, we have in the numerator the difference between the two. Again, use decimals. And then in the denominator, we have the square root of our pooled percentage. So 0.51, 1 minus 0.51 is 0.49. And this would be times 1 over 150 plus 1 over 50. And quite a formula there, but we can throw that into a calculator to approximate our Z statistic. So let's see what we get. So 0.74, let me use parentheses on the numerator, 0.74 minus 0.28 should go on top. Then that's all going to be divided by the square root of 0.51 times 0.49 times 1 divided by 50 plus 1 divided by 50. Let's make sure we get it all in there. I think that looks okay. Make sure to close my parentheses. I think I closed them all. And there we go. So we would get a value of 4.6. And again, that's like standard deviation. So that's a super, super high Z. Remember, 2 to 3 is already getting pretty high. And again, we could look up in a Z table what that means. That's actually so high that it's not even in our Z table. Which again, if you go towards like the very end, 3.4, notice we're already at the 19.99999 p-value. And technically, we want to, when we're looking at probability, again, if we were to look at the null and alternative hypotheses here, we should probably write those out. So let's go ahead and do that. The null hypothesis is that those proportions are equal. P1 is equal to P2. And our goal is the alternative hypothesis is that they're not. And in this case, our goal is to say that P1 is greater than P2. because it's asked if men, which was P1, were more likely to date younger people. So this is actually a one-sided test. And again, we could use a calculator to check this out, but it's going to basically be, it's so high. It would be our p-value. Again, you would want to use the negative score because it's the extreme probability, which is going to be less than 0.0003. So if we go into our two proportion Z test, again, because we have two proportions here, and we're comparing them, and we're doing a significance test, and type all this in. So we got 37, 50, 14, 50, and we want to do the fact that P1 is greater than P2. I'm going to calculate, and what we get is our Z-score, and our probability is 2.16 e to the minus 6. And I wanted to mention, if you ever see this, this is how the calculator represents scientific notation. So the p-value we get here, again, this is capital P, not lowercase p, is, well, let me just write this out. It's 2.11 times 10 to the negative 6 is what that means. Or basically that means move the decimal places 6 to the left. So, because again, the p-value should never be more than 1. It should be something between 0 and 1 because it's a percentage. But it should be, in this case, it should be 0.00000211. And that's a super, super small p-value. Again, as we kind of knew, that data was very, very different. It was very unlikely for that to be attributed to random chance. And what we've seen is that there is, less than this would be 1%, 1/10, 1,000th, 1/1,000,000th of a chance, assuming I did that right, but you get the point. Very, 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 very small chance of this actually occurring, which is definitely less than any alpha for a significance level like 0.01, or, something even smaller, 0.001. Displays super, super unlikelihood. So again, since it's less than alpha, we'd say that yes, this is statistically significant. And our conclusion is that we reject the null hypothesis. Meaning that we reject the claim that those were equal. Again, we have not proven that they're different, but we are pretty darn sure that they are.